about this state. It's completely new to you. And you won't know anything about this state either. Right? So the idea basically being that small changes to states will give you a new state number. You know, state 15,975 versus state 15,869. You have no clue how those states are different, are similar. Do you see what I'm saying? So to do a good, so there is this notion of compression, and there is also the notion of pattern finding. I want to be able to generalize what I learned about the state and say this is actually applicable to the state. Even though the states look different, they, in some sense, their structure is the same. Okay? Now, first of all, I want you to remember in the back of your head that compression and prediction are both great motivations for generalizing, for learning. And in fact, one of the interesting things is every compression algorithm you found in your life is probably a kind of a learning algorithm. What compression algorithms do you know? You never compressed anything? What else? JPEG. Who said JPEG? Okay. So, you people obviously are not wasting your time watching pictures, right? You know, JPEG, MPEG, MP3, what are all those things? They're all compression algorithms. Okay, now, ask yourself the following question. What's the difference between JPEG compression and zip compression, .zip? Not you, somebody else. So, as anybody, you haven't even seen pictures, why would I want to hear about it? So, what do people think of using zip for reducing the size of pictures? Have you done this? Zipping doesn't seem to go anywhere, right? So, JPEG actually does, in some sense, a different kind of a compression than zip. Why don't you use JPEG on your directories? So, at the end of the semester, essentially, my suggestion is that you just take a JPEG or an MPEG compression of your class directory. In fact, before that, I mean, end of the semester, it doesn't really matter to you. So before the midterm, you know, just take a MPEG compression of your class notes. Why won't you do that? It is compression, but it's lossy compression. JPEG and MPEG, they're all lossy compressions. Zip is lossless compression. Zip basically you can compress and you can bring it back. JPEG and MPEG, once you do the compression, you can never get the original back. How many of you actually have like an SLR camera? Okay, so there is a RAW mode. Why do they have the RAW mode? Because without the RAW mode, they just store the JPEG. And if you have the JPEG, you can't go back to the RAW mode. Whereas if you have the zip, you can go back to the directory anytime. As you think about learning in this class, for the next several classes, think of compression as something extremely connected to learning. Because after all, that's how we got here. We said we want to represent the value function in a more compact fashion. So an important thing that you want to understand is, yes, it's closed compression. In what way is learning different from compression? You see what I'm saying? First you understand it's connected to compression, but in what way is it different from compression? It turns out that one of the biggest points about learning is the ability to generalize to unseen states. Even at the risk of being lossy on the compression that you have done up until now. Do you understand what I'm just saying? So imagine during your reinforcement learning, at some point in time you have out Q values, somehow you compress them. Okay, if you compress them using something like zip, you can decompress them, uncompress them, and you get exactly the values that you have seen. So your ability to reproduce the data that you have seen is, fully 100% accurate. But on the other hand, that kind of an idea, zipping is not going to help you with the problem that I have here. It will just give me all the states back with their exact value functions. What I really need is the ability to predict the unseen states that I haven't seen before, but I would like to say they're similar enough that their value is similar to the true value for this action, for this state is similar to the other one that I've seen. So one of the big things in learning is this tension between compression and ability to predict. And it comes up in many, many, many different names. One particular name, one pretty fancy name is bias variance trade-off. We'll talk about this again. Other is training versus testing error. Okay, if you have done, how many of you actually played with any sort of, before this course, how many of you have played with any sort of learning algorithms, like supervised learning algorithms? So those of you who did play, in the training case, essentially there is a training error. Okay, and one of the interesting things is a learning algorithm which has 0% training error is not necessarily the best learning algorithm. What really matters is the test error. And typically we know that the test error is sort of correlated with the training error. If training error is too high, test error is also likely to be too high. But if you drive down the training error too low, then in essence you are compressing the data without seeing any patterns in it. So this, another name for that is, if you compress, you call it overfitting. These are all the jargon. If you want to just sort of get one of these Google jobs and you don't want them to, find that you don't understand everything, throw in words like overfitting and compression and all this stuff, and we'll be talking the right lingo. And hopefully, while you're doing this, you also figure out what they are. Okay. So basically, overfitting is what good compression is supposed to do. You're so happy that zip is an overfitting algorithm. Otherwise, it won't bring back your directories. It will bring back some noise which looks from far away as the image of your directory, which is no good. Okay? So, anyway, so we keep this in mind that, suddenly we now are in this area of understanding how, learning issues, supervised learning issues work. So, what we want to do in essence to provide both good compression and good prediction is you essentially go towards algorithms basically which are sort of, one idea would be to first of all represent states in terms of some features. Because you need to be able to see that this state and this state are similar. If I just give you their social security numbers or their state numbers, how can you tell that they are similar? You need to know their content. How do you talk about content of the state? We give them some features. The following features represent the state. Okay, now what are a reasonable set of features? For example, in Pacman, you could say distance to the closest ghost, distance to the closest dot, number of ghosts, 1 over the distance to the dot square, that's another feature. Is Pacman in a tunnel, that's another feature. So for each state, there are a bunch of these features. Now, as you're saying this, you might be wondering, how many features am I supposed to have? There's no quite answer to that. Okay, you essentially decide on some number of features and say, that's a good enough representation, I'm going to go with it. Okay, so for example, how many features? So one idea is that I decide your grade based on your social security number at the end of the class. And obviously that is foolproof because your social security number is you. Nobody else has that social security number. But on the other hand, it's extremely hard to tell how this social security number's grade is connected to this other social security number's grade. So then I come up with some structure for representing you guys. You know what you are for my class? The columns. The homework 1 score, the homework 2 score, the homework 3 score, the project 1 score, the project 2 score, the project 3 score, the exam 1 score, the exam 2 score. Is that enough? Remember, I started this class thinking I'll have 3 exams, but then we decided that I'll choose good enough. So already there is no such thing as a single feature representation. with respect to the features I have, I will make my decisions. But at least in this feature representation, I can say this student seems very similar to this student in terms of their grade. And then I can decide that their grade should be similar. Do you see what I'm saying? Okay, again, this is the stuff that you do all the time. I'm just asking you to reinvent this. You have to realize that what we have been doing until now is atomic representations where this sort of comparing two states was not possible. Now we have feature-based representations. These are essentially called lifted representations. In the beginning of the semester, I talked about atomic, propositional or feature-based and relational representations. And I said atomic can be thought of, let's say, as the machine language, and propositional or feature-based can be thought of as sort of a C language, assembly language, and relational can be thought of as object-oriented languages. So we're going in that direction right now. This is the first time we came to talking about representations of the states that take into account what's inside. So essentially you sort of figure out what are the states for now. Okay, and then of course once I have these states, then I define the Q value of a state as some function of its features. Some function of its features. Do you see what I'm saying? So the idea is the following. Imagine the following. Again, going back to the exam scenario. Imagine you're trying to figure out, you are my TA right now, and you're trying to figure out how to give grades this year. Okay? But you happen to have training data from last year. Training data from last year are all the students with their homework scores, exam scores, and their project scores. And the grade that I wound up giving them. Okay? So then you are essentially trying to figure out how to decide the grade here. And so you would say, I'll try to learn a function that Rao seems to be using, which is, some grading function saying alpha times the homework score, weight 1 times the homework score, plus weight 2 times the project score, plus weight 3 times the exam score. If it is greater than or equal to some magic number, weight 4, then they get this grade. If it is greater than, if it's below that and greater than or equal to this other number, gets this other grade. That's a functional representation of the grading scheme I use. You learn it from the data, and then you just apply it to the new data. That's what we'll do for Q learning now. So Q learning basically, as you're doing Q learning, you both have this view of states as atomic as well as states as having feature representations. From the atomic point of view, you know exactly what is the new value of the neighbor, what's the value, the current value of this state, what's the current value of the neighbor's state. Okay, using that you know how to update the Q value. And then you convert that into a functional form in terms of these weights. We'll talk about it. That's the general idea that you're going to do. The tricky part in the exam scenario is figuring out what alphas did I use in deciding my grades last year. What weights did I use in deciding my grades last year? You have to figure those weights so that you can then decide the current semester's grades correctly. Do you understand what I'm saying? Okay, and then in doing so, you try various weights to make sure that the grades that you have actually seen in the training data are actually correctly predicted. And the weights that are actually predicted in the training data completely correctly are probably like high compression. Okay, and so if you use those weights as something close to predicting the previous grades correctly, in the new scenario, then you are able to essentially generalize my algorithm that was inside my head to this new data. Okay, so that's basically what we are doing, and in essence, an idea would be that we will consider a notion of a function approximation. The function is any arbitrary function. For the exam grades, I just made up this thresholding function. Weight 1 times project scores plus weight 2 times homework scores plus weight 3 times exam scores greater than or equal to some particular threshold, which is another weight. And I need to learn all these weights to make sure that it is predictive of the grades I gave last semester. And once you figure this out, then you can just predict everybody's grade. Do you understand what I'm saying? Okay? Now, figuring out those weights, of course, requires search, right? You try a set of weights and see if it actually predicts the grades that people got last time correctly. So, for example, imagine you said weight 1 times homework plus weight 2 times project plus weight 3 times exam greater than 0, A plus. Imagine that's the idea that you came up with. It's a good idea, but it's also a bit of a wishy-washy idea. You will find that last year there aren't, by your function, everybody should have got A plus in the last year's training data, but not everybody got A plus. So clearly these weights are wrong. So you need to try a different set of weights. An idea is just try a whole bunch of different weights for each of. Imagine in this particular exam case, all I really have is, imagine I'm just trying to figure out A grade, okay? So W1 times H1, which is HW, homework score, plus W2 times project score, plus W3 times exam score, greater than or equal to W4, then A. This is the rule that you decided I'm using. All you need to figure out is, you notice that these are the features. Right? Each student is represented in terms of their homework score, their exam score, and their project score. Those are the features. It's no longer the social security number. It's just these values of their homeworks, exams. And then you just have to figure out these correct weights. These weights such that they will be correctly representing last year's, correctly predicting the last year's training data for which you know the answer. And if you did that, then you can use it for this year and hopefully you can predict. And as I said, you need to try different values for these weights to see which set of weights will wind up being the closest to the best in predicting last year's weights. Right? So why don't I try the following thing? Loop over all the weight configurations. Try a configuration, see if it is good. If not, try the next one, try the next one, try the next one. To do that, that's a search. To do some sort of an A-star search here. The huge problem, of course, is we are, first of all, in a continuous space. The weights are continuous. And it turns out that weights are continuous, and it turns out that essentially what I'm trying to do is optimize, find an optimal point in the weight space. And it's suddenly continuous search, so the only game in town is calculus. It's a continuous function, you don't do A-star search. Okay? So that's basically the idea of function approximation. In particular, we will assume that these are the features for, let's say, for the Q learning. These features for Pac-Man are, let's say, this is how close to the dots, how many ghosts, and so on and so forth. Different features. Who came up with those features? For now, I'll assume you just came up with those features. You understood Pac-Man the game, and you came up with those features yourself. Okay? So then all I need to do is, again, I'm going to list of weights, W1, W2, etc. In this slide, I'm using the symbol theta. It's like a fancy way of, you actually, if you use theta, you tend to be taken more seriously in machine learning. Okay. So instead of saying weight like some normal person, say theta. It's like the same thing. Apparently, many years back, there was a TV show about Bible on NBC, and then all the pagans and heathens were talking in the Midwestern American accent. Jesus himself was talking in great English accent. Right? So you kind of know that you have to speak in English accent. You have to use theta to be taken seriously. Okay, so thetas are just weights, and you need to find these thetas. Don't be put off by theta. It's just weights. Okay? And then of course I need to find what's the best value of theta. And as I said, I will have to find it by gradient. And by calculus, basically the idea of calculus that we use here is gradient descent. Okay, so here's the idea basically for temporal difference learning. Let's say just do the TD first, okay? TD for RL, and then you can also generalize it to Q. So you start with the initial parameter values. That means you sort of set some values, thetas, for these ones. And then you keep changing the theta slightly. So the same thing in the exam scenario, I start with some values for the weights, see the training error, nudge the weights in the direction that reduces the error. Don't take big steps, take small steps. The question is, what is the direction in which the weights have to be changed? Notice that you're changing all the weights at the same time. So what you're actually doing is multivariable function optimization, maximum or minimum of the multivariable function. So all of you, after taking single variable calculus, you did, many of you have done multivariable calculus. Okay, and in single variable calculus, you know that optimum has to be found by taking the derivative and setting it equal to 0. Here you find the stationary point by taking the partial derivative with respect to each of the variables. Now, by the way, in this case, what are the variables? Okay, how many people say that the HW, PR, and X are the variables? Raise your hands. How many people say W1, W2, W3, etc. are the variables? Make sure you understand that. Okay? So the weights are the variables. We are now looking in the space of, for every different weight vector, there is a new function. And you're trying to find the best function that will have the, kind of the least training error for now at any rate. And then assume that that will also predict the future. Okay? So it turns out then that actually you have to be able to see the biggest loop, the intuitive leap that you need to do is essentially to realize that this is a multivariable continuous function optimization. So finding the values of theta involve finding the place where gradient becomes 0. And those are the places that might be minimums and maximums. And some of them actually might be stationary points too. Do you guys remember stationary points, saddle points, and all that stuff? Okay. So minimum actually, so the necessary condition for some point to be a minimum involves setting partial derivatives to 0. But that's not sufficient. Sufficient requires taking the second order derivative, for example. Okay. Again, it all should be coming slowly back into your head from the old days of calculus. Okay, so then essentially you're updating the thing, and then updating now means, remember in the state function, in the atomic function, atomic representations that we use for MDTs, that temporal difference learning just changed the values of each state a little bit at a time, directly. Now you don't change the values, you change the weights, which will indirectly change the values. So imagine there are 10 million states, right? So during temporal difference learning, you are nudging each of these 10 million states have their values, current estimates, and you're nudging them to be correct. 10 million of them. Now imagine you decided that these states all can be represented in terms of exactly 15 features. Each state can be represented in terms of 15 features. So then what happens is you're no longer changing 10 million quantities. You're changing 15 quantities. Now the thing that also means, what that also means is now states are going to be entangled. In the past, and I hope you understand this, try to follow me. In the past, when you change the value of state 1450, S1450, that guy's value changed, nobody else's value changed. But now to change S1415's value correctly, you wind up changing these thetas. That also affects everybody else's value. Go back to the exam scenario. Imagine that the reason that you did not like, you started with this to be 0. Let's say this is 1, 1, 1, and 0 is the initial configuration you came up with. And then you looked at one particular student. That particular student you said should have grade A plus. They didn't have grade A plus, they had a grade F. Okay, so there's a difference. And you need to change the weights here such that that particular student's grade would be correct. But when you change this, you are now essentially changed the way everybody else's grades are also being decided. Do you see this? This could be a bug or a feature. It's a bug in the sense that guy didn't do well in projects, and so you are somehow reducing the weight for projects. But I did well in projects. How come my grade is going down? Because of him and other. But that's what it will wind up doing when you are actually fitting these weights. But the entanglement of states in terms of these weights is what gives you the generalization capability. Because you are not just changing one cell's value, you are essentially changing the values estimates for every other factor. That's what is happening in learning. Okay? Okay, what just happened? I hope you kind of figured out what happened here. Two things changed. There are like two pivots with respect to the rest of the semester. Just a second. One is we pivoted from atomic representation to feature-based representation. And in particular, for now, we assume that the features are hand designed. An interesting question might be to essentially give a lot more information than the hand designed features and let the learning algorithm figure out what are relevant and what are irrelevant. Okay, even if I give you a lot of features, you might wind up saying, for example, a feature is irrelevant if you wind up finding that the weight for that feature is 0. Imagine the best way to predict last semester's grades involved, an expression where the weight for the exam scores is 0. Which means you realize by learning that exams don't seem to matter in last class. You see what I'm saying? Now you really like to have the training data from last year, so that you can figure out how the grades can be predicted. Okay? So for now we assume that basically hand-coded features are given. But one of the interesting things that can be done, more ambitious thing that can be done, is let the system learn the right features itself from the raw input. In particular, if in fact the states are given, let's say, as an image, which partly what AlphaGo wound up doing, okay? It took the picture of the board. If you, it looks as if when you have pictures, so for example, if I'm doing the same kind of a thing for deciding, given a picture, how beautiful is the person in that picture. Like suppose I'm doing the original Mark Zuckerberg's heart or not before the Facebook, but I want to do it by removing people from the, they don't get to vote. I just use the existing beauty formulations to figure out how do people seem to decide, given a picture, whether that, what is the scale of their beauty of that person, from whatever 0 to 10. Okay, now the interesting thing there is you may not know even exactly what features to give. And one thing, the quote-unquote deep learning is different from other kinds of shallow learning, is that they try to learn the features along with the weights. It again can be a bug or a feature. Okay, if the system is learning its decisions based on the features that it extracted and you have no idea what it extracted, you have no clue what you're supposed to be doing. So remember, this is all with respect to my showing this this study of taking people's pictures and predicting their sexuality. That somebody did recently at Stanford. Okay? Now, what did the system learn? What exactly was it using? It seems to be good. It has 78% accuracy in predicting the sexuality of the new pictures. But exactly what did it learn? It learned some features. And then that becomes, on one hand it's good because you didn't have to draw features. You had no idea what features are actually representative of, concepts like sexuality. And just as you don't know exactly what features are representative of concepts like cat, you might think that I know exactly a cat. You only know a cat when you see one. If I ask you to give me a set of features that define a cat, you would be hard pressed to give some features. So there is no hand design. That's where in vision in particular, hand designed features have basically been a bit of a problem, and the deep learning model being quite useful. But where we know how the actual training is supposed to work we can give some of the information about the problem. So what AlphaGo wound up doing is combining both. It basically has some hand-generated features that are based on the actual game itself, and some other features that are just automatically derived by the training algorithm. So that's one thing that we changed. The second thing we changed is we are essentially now in trying to compute the weights for the features. I try to make you understand that now instead of trying to figure out individual values for each of the states, I'm trying to find out a function that predicts all their values correctly at the same time, depending on their feature values. And so that means you're searching for the weight values. And searching for the weight values is a continuous search, and you have to do gradient descent. Okay? Now it turns out that there is an idea called hill climbing, which also does this kind of. So one thing that you have to understand about gradient descent is, unlike A-star search, which kept track of all the possibilities that it hasn't yet evaluated on the open list, and made sure that it went through the open list and only stopped when in fact it picked the goal node to expand. Right? That's what A-star search did. That's how it guaranteed that when it stopped, the solution it found is actually optimal. What gradient descent instead does, essentially, is taking the vector of partial derivatives, that's what I was explaining in that write-up, and then makes a step in the direction opposite to the direction of the partial derivatives. Partial derivatives would be a vector in this high-dimensional space. And they will be pointing in the direction in which the value of the function is increasing the fastest. And so if you take a little step in the other direction, that would be nudging the weights in the right direction so that they will come towards reducing the function value. And typically we consider function values to be error that you're minimizing. And so you want to minimize. Okay? So one important thing about this is that this search is very different from A-star search. Of course, there are derivatives which you never have to deal with in A-star search. But actually, this is not just, that's not the only difference. I want to show you a problem that does something like gradient descent in discrete space. Not continuous space, but discrete space. This is the famous problem of n queens. For those of you who understand chess, okay? So given an n by n board, place n queens on the board such that no pair of queens are in conflict. And you understand the way queens move in chess, right? So if you put one queen here, another queen in the same column, or row, or diagonal, they will be in conflict. You see what I'm saying? Okay? So you need to find a placement of queens on this board such that no pair of queens are conflict. Okay? And so